In this video lecture, we tackle the last of the three scenarios from section 9.5, which is a hypothesis test for a mean when the population standard deviation is unknown. We talked about this scenario for confidence intervals. When you don't know the population standard deviation, you approximate it with the sample standard deviation. And we learned in Chapter 8 that it's better to use the t-distribution in this case rather than the normal distribution. We're going to do the same thing for the hypothesis test. When you've used the sample standard deviation as an estimate for the population standard deviation, it's better to use the t-distribution when you're calculating a p-value in a hypothesis test. So the calculator function we're going to use is called TTest. Let's lay out our 6-step procedure for this scenario. The first step in a hypothesis test is to determine the hypotheses, and the hypotheses here will look the same as they did for z-test because this is still a hypothesis test for a mean. So the null hypothesis will be a claim that the population mean is equal to some number, and we're going to use that u sub 0 notation again for our number. The alternative hypothesis will somehow contradict that with an inequality by either stating that the mean is not equal to mu sub 0, that the mean is less than mu sub 0, or that the mean is greater than mu sub 0, and the choice of inequality is dependent on the claim in the problem. Second step is to identify the level of significance, which we denote by alpha. Step 3 is to collect evidence from the sample that you gather. We're going to need 3 pieces of sample evidence here. We're going to need the sample mean, which we denote by x bar. We're going to need a sample standard deviation. Since sigma is unknown, we're going to need to use s as a point estimate. So we'll have to find the sample standard deviation, and we'll need the sample size. Next, we compute the p-value, and we're going to do that with the calculator function TTest. We're using the t-distribution because we have the sample standard deviation and not the population standard deviation. The calculator is basically going to say, okay, let's assume the null hypothesis is true. What is the likelihood that we could have witnessed sample statistics like this in a t-distribution for that given sample size under that assumption? If that probability is small, then we don't believe the null hypothesis, and if that probability isn't so small, then the null hypothesis is at least believable, it's plausible. To determine what's small and what's not small, we compare the p-value with the alpha that we found in step 2. Same rules as before. If the p-value is less than or equal to alpha, we will reject the null hypothesis. We'll consider that p-value to be small enough to risk making a type 1 error, and we'll reject the claim made by the null hypothesis. If the p-value is greater than alpha, well then we're wary of making a type 1 error, and so we'll fail to reject the null hypothesis. The last thing I ask you to do is write a conclusion. We're going to write some sort of interpretation that sums up our results. We already have experience with this, so we're ready to jump into examples. A study is conducted on a new treatment for migraine attacks. For the general population, the mean duration of a migraine attack is 16.4 hours. A random sample of 15 migraine patients is selected to participate in the study. The sample had a mean duration of 13.6 hours with a standard deviation of 10.5 hours after receiving this new treatment. Assuming the durations are normally distributed, test the claim that the mean duration of migraine attacks is reduced by the new procedure. Use alpha equals 0.05. This is a standard real-world application of hypothesis testing. We've got some sort of new medical treatment, and we want to see if we can show that this new medical treatment is effective in some way. In this instance, we're testing the claim that this new treatment will reduce how long somebody has to suffer from a migraine attack. The average for the general population is 16.4 hours. They selected 15 patients at random, and the mean duration for that sample was only 13.6 hours, almost 3 hours less on the average. But that was just for a sample of 15, so the question is this data statistically significant? Can we confidently say that this will reduce the mean duration for all patients? That's where the testing comes in. We can tell this is a hypothesis test because we're being asked to test a claim. So our first step is to come up with the hypotheses. We need a null hypothesis and an alternative hypothesis. We're being asked to test the claim that the mean duration of attacks is reduced by the new procedure. So if the mean is reduced, then it's less than what it used to be before. And according to the second sentence of this problem, for the general population, the mean duration of a migraine attack is 16.4 hours. So one of the claims in the problem is that the mean is less than 16.4 with the new treatment. That has to be the alternative hypothesis because remember the alternative hypothesis is the one with the inequality symbol. The null hypothesis will make a claim about the same parameter and compare it to the same number, but the null hypothesis is always an equation. It's a statement of equality. So the null hypothesis is basically the claim that the new treatment does not reduce the mean, and the alternative hypothesis is the claim that it does. We've got these two dueling hypotheses. Second thing I ask you to do is identify the level of significance. I've put it at the end here at 5%, 0.05. We'll use that to help us make our decision after we've calculated the p-value. The third thing we do is collect the sample evidence, and this being our first example of t-test, let's review what that sample evidence is. We need to identify the sample mean, the sample standard deviation, and the sample size. The sample size is 15. Reading the next sentence, it says the sample had a mean duration of 13.6 hours with a standard deviation of 10.5 hours after receiving the new treatment. So the sample mean is 13.6. We're confident in that. The sample size is 15. Going back to the sentence with the standard deviation, notice that it said the sample had this mean with this standard deviation. That wording indicates that the standard deviation comes from the sample and it's not from the entire population. We have a sample standard deviation of 10.5 hours. And because we have a sample standard deviation, that's why we're going to use t-test and not z-test. In order to use z-test, there would have had to been specific wording that tells us that this is a population standard deviation. Maybe it would have used the phrase population standard deviation. Maybe it would have used the symbol sigma. It needs something to indicate that it's the standard deviation for all of them. This sentence very clearly says that this standard deviation came from the same group that gave us this mean of 13.6. And that 13.6 came from the sample, so the standard deviation also comes from the sample. T-test works a lot like z-test. To pull it up, you press Stat, scroll to Tests, choice 2, right underneath z-test. Make sure you're in stats mode because we have the statistics. Mu sub 0 is the number in the hypotheses, 16.4, which is the mean duration for the general population. X bar is 13.6, that was the mean duration in the sample using the new treatment. Notice that the calculator specifically asks for S as if to say, hey, if you're using me, then you must have only known a sample standard deviation and not the population standard deviation. Z-test specifically asks for sigma. The sample standard deviation was 10.5 hours. The sample size was 15. And the claim in the problem is that the mean has been reduced, which means it's less than what it was for the general population, so we want to select the less than symbol. To recap what's going on here, 13.6 is clearly less than 16.4, but we're taking this from a sample of size 15. Oh, I forgot to point this out, but we have a small sample size, but it's okay because we're told that the durations are normally distributed. Getting back to the issue at hand, the question here is this data statistically significant? Can we use this sample to confidently say that the mean duration of migraines under the new procedure will be less than it is for the general population? We'll calculate. First line you see is the name of the test, more important than ever now that we're up to 6 different calculator functions in this unit. Second line should match your alternative hypothesis. Let me pull that back up. Second line matches the alternative hypothesis. Next line is the test statistic. You can ignore that because we're doing a p-value approach. The p-value is around 0.16. The p-value is basically saying that if the null hypothesis was true, the percentage of samples that could yield data this extreme for samples of size 15 is around 16%. It would not be uncommon to see such a sample if the null hypothesis was true. Therefore, we aren't able to reject the null hypothesis. Looking back at our rules, the p-value is greater than the value of alpha that we have. We were given an alpha value of 5%. The p-value exceeds that, so we failed to reject the null hypothesis. If we can't reject the null hypothesis because it's too believable, then we can't support the alternative hypothesis. It's not to say that the alternative hypothesis is false. That's not our claim. Just like we're not saying that the null hypothesis is true. We're just saying there's not enough evidence to support the alternative hypothesis. And that's basically how we write our conclusion. There is not enough evidence to support the claim. Now I just see what the claim was in the problem. That the mean duration of migraine attacks is reduced by the new procedure. While the sample evidence certainly points in favor of the alternative hypothesis, it's simply not strong enough for us to be confident to say that that's a true statement. Again, we're not saying the alternative hypothesis is false. We're simply saying there isn't enough evidence for us to be confident that it's true. Let's look at another example. A high school institutes a new prep course for the ACT test. Historically, the mean ACT score at this school has been 21.3. A random sample of 22 students who took the new prep course scored a mean of 23.1 with a standard deviation of 3.8. Does this data provide enough evidence to support the claim that the mean ACT score is higher for those who take the new prep course? Use alpha equals 0.05. You may assume the scores are normally distributed. We're being asked if we can support a claim, so this is a hypothesis test problem. Step 1 is to come up with the hypotheses, H sub 0 and H sub A. The claim in the question is that the mean ACT score is higher for those who take the prep course. Higher than what? Well, than the historical average, which is 21.3. So the alternative claim is that the mean is greater than 21.3, greater than the historical average. I know that has to be the alternative hypothesis because it's an inequality. The null hypothesis will be the claim that the mean is not any different than the historical average. In essence, this claim is that the prep course really has no effect, that the average is still the same as the historical average. The value of alpha is 0.05. I know I've used that twice now. That is the most common value of alpha. Step 3 is to identify the evidence. A random sample of 22 students. There's our sample size. I know that's less than 30, but we're assuming the scores are normally distributed, so we're covered there. Who took the new prep course scored a mean of 23.1. That's the sample mean because it comes from the 22 students, with a standard deviation of 3.8. That's the sample standard deviation because it also comes from the sample of 22 students. So the sample mean is 23.1, the sample standard deviation is 3.8, and the sample size is 22. Because we have a sample standard deviation, we're going to use t-test to calculate the p-value. We're going to use the p-value to make the determination if the data we gathered is statistically significant enough to conclude that the mean has increased from the historical average. Is this prep course effective? It certainly looks like it might be because the average in the sample was almost 2 points higher than the historical average, but we're doing this for a sample of size 22. We saw in the previous example a sample mean that was almost 3 units below the number in the hypotheses, but that data wasn't statistically significant, and that had to do with the small sample size and the standard deviation. Here we have a slightly larger sample size and a much smaller standard deviation. Maybe this will be statistically significant. Let's check it out. T-test is choice 2 on that test screen. If you press stat and scroll to tests, it's choice 2. Mu sub 0 is 21.3, the historical mean score on the ACT at this school. X bar is 23.1, the mean of the sample who took this prepped course. S is 3.8. N is 22. And the claim is that the mean has increased, so we want to choose that last option. Scroll to calculate and hit enter. First line is the name of the test. Second line should match your alternative hypothesis. Third line is ignorable for our purposes. It's the p-value that we're after, and it's around 0.019. This p-value is around 1 in 50. Basically, the p-value is saying that if the null hypothesis was true, the probability that we could have gathered sample data as extreme as what we witnessed with these characteristics is around 1 in 50. It just wouldn't happen very often, so the null hypothesis isn't very believable. Using our process, we just say the p-value is less than alpha, and so we're going to reject that null hypothesis. We feel we can safely reject the null hypothesis because the p-value is so small. It means the null hypothesis just isn't a very believable claim. Well, if we're rejecting the null hypothesis, then we have to replace it with some other claim, and the evidence points in favor of the alternative hypothesis. Our sample mean was greater than 21.3, so we feel comfortable supporting the alternative claim. There is enough evidence to support the claim made by the alternative hypothesis. And what was that claim? Well, let me see what it was in the problem. That the mean ACT score is higher for those who take the prep course. Another way to say that is there is enough evidence to support the claim that the mean ACT score for those who take the prep course is greater than the historical average, or is greater than 21.3. So in those two examples, we saw one way that we use hypothesis testing, which is to compare something that happened in the past with results from a new procedure, whether that's a new way to treat a migraine or a new way to prep people for the ACT. Another way that we use this is to just make inferences when there's not a whole lot of data available. This happens a lot in biology, so here's a biology example. Biologists discover a previously unknown crayfish in Alabama. A random sample of 16 adult crayfish of this species has a mean length of 10.6 centimeters and a standard deviation of 1.24 centimeters. Does this sample provide enough evidence to say that the mean length of all such crayfish is longer than 10 centimeters? Use 0.05 as your significance level. You may assume the lengths are normally distributed. So if this is a new species, a creature that they didn't have access to before, there isn't going to be a whole lot of data on it. One way to make an inference would be to make a confidence interval, and that's not a bad idea, but we're going to do this from the perspective of hypothesis testing. Let's make sure we understand what we're doing here. We were only able to gather a sample of 16 of these crayfish, and their mean length was 10.6 centimeters. So obviously the mean of the sample is bigger than 10 centimeters. That's not the question. The question is, can we be sure that the mean length of all crayfish of this species is longer than 10 centimeters? Not just the ones that we've captured, but every single specimen that would exist. We don't have access to all of them, so we can't calculate the population mean. We're making an inference based on the sample that we've gathered. Okay, we're being asked if the sample provides enough evidence to make a claim. It doesn't use the word claim here, it says say instead. But same idea. We're testing a claim. The claim in the problem is that the mean is longer than 10 centimeters. The null hypothesis would be that the average is equal to 10. The value of alpha was set to 5% again. Standard value of alpha, easily the most commonly used value of alpha to determine if data is statistically significant. They sampled 16 adult crayfish of this species. That's the sample size. We're good there because we're assuming the lengths are normally distributed. The sample of 16 adult crayfish had a mean length of 10.6, and that sample also had a standard deviation of 1.24. That is a sample standard deviation. It's not a population standard deviation. So the sample mean is only 0.6 of a centimeter greater than the number in the claim. That's not a big difference, and our sample size is very small. But this data might still be statistically significant because the sample standard deviation is also small. There's not a lot of variation in the lengths of these creatures in the sample. And so this data might still be statistically significant. This is why we need the p-value. Unless you've got a lot of experience with this, just looking at the numbers, it's hard to tell if that data is statistically significant. The p-value helps us with that determination. We're going to use t-test because we have a sample standard deviation. Stat, scroll to tests, choice 2. The claim is that the mean length of all of these creatures is greater than 10 centimeters. The sample mean was 10.6. It was bigger than 10, but not by much. The standard deviation was only 1.24 though, so not a whole lot of variation in these creatures. The sample size is 16. And the claim is that the mean is greater than 10, and I get a little bit of joy out of getting to be lazy and not having to change this. Calculate. First line is the name of the test. Second line is the hypothesis that we're testing. Third line is ignorable. Fourth line is what we need. The p-value is around 0.036. Since the p-value is smaller than alpha, we reject the null hypothesis. At the 5% level of significance, we feel comfortable rejecting the claim made by the null hypothesis, and therefore will support the claim made by the alternative hypothesis. The alternative hypothesis was the claim that the mean length of all such crayfish is longer than 10 centimeters, and so we're going to say that we support that claim. There is enough evidence to support the claim that the mean length of all such crayfish is longer than 10 centimeters. That wraps up this lecture. The main sticking point for these is determining the difference between z-test and t-test, so be sure to spend a little bit of time thinking about that. If you have any questions, reach out.